Hello and welcome to the 30 filters assignment. I'm now going to go through my code for it. So first here we see the general functions for Open Frameworks. Then I have this list of functions which I have created. And then we have the initial cam height and cam width. And then of course we have the allocated pointers that is going to find all our pixels, as well as a texture for each. This you see here. Move that. This you see here is the point which I will find the center of mass with, and here are some of the what's it called kernels I will use, which is basically two-dimensional arrays. My idea for this project is to go and show all of them at the same time. So what you will see in the end is actually like a screen full of all of these small cameras where you can actually see everything like in one go. In order to do this, I made all my functions so that they take in the width and the height, and they inside modify the pixels that they get in, basically, so that you send the address ergo pointer to the function of where these things lie, so that you don't copy in them, but that you send them in by reference. So it's basically sending the address in of a pointer, as you can see in one of these here, by saying pointer address. Okay, so let's go through the first one, which is actually let's jump to the to the test app.cpp, and all I have in here is actually just all of this allocates the memory for the things I want to be displayed. It creates the space for it per se. Some pre-made kernels, which is including the general mean value, the Gaussian 5x5, the spell, Laplacian, sharpness, as well as the mean disk number 7. These for loops here are basically going through. They're sending the information from these guys back into the ones I have here in the bottom, which allows me to use them when I send them to my functions, as it is not allowed to create this inside the main inside the test app.h. Going to the update function, which is the interesting, of course. We have the video grabber update, which updates the video grabber, and then every new frame, which means that it will reduce the amount of times this happens, but still make it valid only when it's in the frame. It will basically do all my functions at once, which is why you will see all of them, as well as load in the data from the operations that the functions do into the textures for each. In the draw, we basically have this. Yeah, we draw all of them so that they all fit. I've specified it, hard-coded it always, so that it will be in the same pattern, but they will be. You can change the size of the cam width and cam height, and it will still shrink and do stuff properly there. I have a few interesting way of drawing it here, because this is for rotation, as well as scaling, which is an operation I didn't really have to make a function for, as there already are in Open Frameworks. And then it's just the circle, which is going to be around the center of mass for one of the pictures. I'll show that when I come to showing how it works. And that's it for the general overview of the code. Now to go into the specifics of the functions. Do the flip function. It takes in an unsigned char pointer called output, a width and a height, and what it does is that it goes in, grabs the video picture, grabs the pixel, creates an unsigned char pointer called pixels, and gets in all the pixels from the picture. This is basically the initial start. I didn't make this into a function by itself because I'm continuously using the video mirror, which is my output output texture for most of them. So here we have the actual do the flip of the function. What it does is that it goes through the height and width times 3 to do it for each pixel. Actually, to do it for each color for each pixel. So let's take 0 as example. This here and this here are for the red ones. And what it will actually do is this will give us the location of where the original pixel is, and this will give us the location of where we want the pixel to be swapped to. And then down here we simply just swoop the picture. So what I do here is I say, okay, we stick in 0 times width times 3, which is basically for all the 3 colors in this particular pixel. But it then goes and says plus j. So in this first one, it will be obviously the 0.0 pixel, because the red one is the first one of the 0 pixel. Then what we do for the one we want it to be mirrored to is actually that we want it to be like instead of being that, now we actually want it to be, you know, the last pixel on the width, because it's we do it like vertically. So there we go. And what we do is we go in and say, okay, so the mirrored one is gonna be at the location 1 times, well, this is 0. This is what we basically talked about just before, times w times 3, which in my case is width is 160, so it's gonna be like 400 something, minus j minus 3. The minus 3 is for moving it back to the red value, so that we know that when we reach the end we're basically in the opposite end when you move all the way to the width. So you start at 0 and you go to 400 something, and then you move back 3 steps to get to the red value. That's why we know that this particular red value is going to be switched with this particular red value. And there we go. The switch happens, and you can see the flip. Okay, as for the next function, this is of course erosion. What I do is I give it in a size of how large my erosion should be, which is should be either 3, 7, 3, 5, 7, 9, 11, whatever, it goes up that way. Then an input, just as explained in the beginning, like give every one of these the address of the ones I have created to make sure that it only uses like half power, so I don't copy everything to my functions, but that I rather just do the operations on the actual things I've already made, because otherwise I probably wouldn't be able to have everything running at the same time due to computer power and shit. What it basically does, it goes through this particular small piece here is what makes the dark edge, in a sense. You actually don't see it usually, but it makes sure that the filter stays inside inside the picture, so that when we move to the edges, it won't mash up and create funny looking stuff around the edge, but rather just, you know, black. We set the sum here for 0, which is basically you reset it every time to make sure that it doesn't continue to count up. This is for what happens is when we reach the white values is that we apply the kernel and we say, okay, so if we sum up everything from within around the pixel. So when we hit the first pixel, we will say, okay, everything around it plus equals the input divided by 255. This is to check whether or not this here is to check if it's a 1, basically. Because if this is 255, it will of course always be 1, so you'll add up by 1. Now, then for down here, it's basically erosion is by fit. So what we do is we say, okay, obviously for every time this will be the size of the kernel times the size of the kernel, both sides of it in a sense, if I want all of them to be in there, and I do in this case. So in the case of, let's say, pop in 3 here, it will be basically 9. So if the sum reaches 9 for that particular pixel, then it will output where we are a white. If not, then it will output a black. This will basically erode it, which erosion it, or how you say that. When you use erosion, you will make the white area smaller, because you will chip off the ends. It's only if everything is white it will. Yeah, only if everything is white there will be a white. So every time you hit an edge, it will chop off like a pixel. Moving on to the dilation, this is very much similar to the erosion, except it does the opposite. It does pretty much the same thing. As you can see, it's very similar, except from this little part here, which is the cheese of the cake. It goes in and says, instead of being on a fit, it's on a hit. So if sum is it just needs to be 1 actually. So basically you move through the picture with your kernel, and if you hit 1 white pixel, well, guess what? All the pixels are gonna be basically that. If you in the kernel have just 1 white pixel, well, the pixel you're at is gonna be white. So this will mean that there will be a dilation there, therefore the name dilation. I do the same, send in the size of it, as well as the input and output, and the size of how many pixels the picture are, so it knows the overall size of it. Okay, moving on to make gray. This is a very simple operation of making it making a normal image into a grayscale image, basically. This is called a perfect grayscale, where you take all the value of the red value, the green value, and the blue value, which is these, and divide them by 3. Plus them all together, divide by 3. Then you get the middle, the average gray. You could also just take like one of these, but then it will not be perfect grayscale, as these other things are not taken into consideration. And of course it does the same thing, takes in input, takes in output, so it knows where to get its info from, and it knows which input to change, so it sticks that out. As for tracking, this is a little more advanced. Let's see now. We take in first of all, this is the threshold for it. Then we have the input, the output, of course, and then we have the temp and current. This is because what I'm doing here is basically background subtraction, and temp and current is for is basically the 2 values of the picture before and now. So it's basically checking the difference between those two in order to detect movement, and then of course width and height as always. When we go through all the pixels as usual, and then of course we save. Of course this is in a grayscale image just because, well, to save computer power again and to make it a little bit better and nicer looking. We save in the current the input as the beginning. Then what we do is we actually do the subtraction right here, where we go in and say the absolute value of the temp is the absolute value of temp minus current. If that is less than t, then output 0. If it's higher than t, output 1. Which basically means if there's a difference between the current one and the temporal one, do something. And that's what it does. If there isn't, don't. And then of course, as the most important step afterwards, then we set the temporal to the current value. So we constantly, this is updating the background subtraction image. There's 2 ways to do background subtraction. Either you take like a reference image or a few reference images where you take the mean value of all of them, and then you constantly, like, it would be like taking a picture of a background, like this small area here, and then referring that, so when every time something new comes in, you would minus those two, and you would see that some of the pixels get molded up. In this case, if you stand still, you will become the background in a sense. Only if you move, it will react. I will show you later. Okay, moving on to PixPy to check. Basically, what this does, this is for the what is it called? Center of mass. That's what it's called. The unsigned char input, it doesn't need an output because we only need to have an input in order to do this. It doesn't really do anything to the pixel itself. It's simply just a calculation. What it does is that it creates this pose of point. I have pose already in the main CPP longer down, and then we have this int n. And what we do is we go through with the double for loop as usual through all the pixels in the thing, and then we create this unsigned char temple b temp tb whatever, which gets in the pixel value. Now what it does is it basically just checks if it's white, and if it is, it will say pose this point here. It will give it the position of x and y, which in this case is, funny enough, where we are, and then it will plus n with 1. N is basically the count of how many pixels we have. Then the actual bread and butter comes into play down here when we go in and say, okay, so pose x and y is now divided equal to n. So we will constantly say that if n is more than 0, of course, because if we didn't have this, it will go bananas over. So you can't divide by 0. So this will basically divide all the white pixels we have with the amount of white pixels we have, meaning that we will get 1 pixel, which is the middle one, which is usually the center of mass. And there we go. I will show this later also when I display the actual thing. Which color? This is a filter I used for 3 to be a little cheesy. I made this function which is basically takes in which color you want, which is either 0 for red, 1 for green, and 2 for blue. Then, as usual, it takes in the input-output as well as width and height, goes through all the pixels, and basically takes the output is equal to the output color, which is whatever. Let's say we take 0, and then it's the red one, is equal to the red one. There we go. We filtered all the other values out, which we don't really find relevant anymore, and then we give it only the red values. Inverto is, well, as it is called, we can also remove the O here, and then it's invert. It takes in the input-output as well as width and height, goes through all the pixels as well as all the colors here, because I was lazy and didn't bother to write anything. And what you do when you want to invert stuff is you take the color, the pixel value on the color, and you say 255 minus the input. This will basically make that you get the exact opposite color of what you would have gotten, which means that it becomes inverted. Okay, and that's pretty simple. Find color. Interesting fun. I've used this in conjunction with which color, just to show that you can find each and every one of these colors very easily, and just made a switch case for each. You get in what color you want. Obviously, it's the same. Input, output, and width, just as usual. Goes through all the pixels. Goes in and say, okay, we make these unsigned chars to be able to say that it's so I can use them in this small if statement here as a shababity, either white or no. So let's go through it. In case we take case 0, what it would do is that it will go in and say, okay, we say that the unsigned char result, which is going to be stuck into all of these, so it will be a black and white picture, is gonna be if R, which is the red value, is bigger than green and blue plus together. So that will mean that if red is, we can assume that we are in a very high area of red, which is where we want to be, and then we make that white. And if we aren't, we make it blue. We make it black, of course. This goes basically for the same for this one. I found out, funnily enough, that it doesn't really work for green, which is interesting because this particular formula for finding color works very great for blue and red. Not for green though. So I changed that to if green is higher than blue and higher than red. Slightly the same thing-ish, but not really. And it actually works relatively okay as well. And that's about it for that function. Cropper is of course cropping. What I do is I go through the usual shenanigans of having the color I want. Actually, nope. This is not for color. This is for basically crop size. What I do is I go in and say, okay, this is not like a smart crop. This is just from the edge to the middle, and it's applied like here. When you go through all the pixels, basically what I do is I don't. So I say if I stick like 10 in here, it will start at pixel number 10 and pixel number 10, which means it will start like further in on the picture and actually not do it for the rest. And basically what it does is simply just takes the output is equal to the input. But this here, this is the bread and butter of the simple crop. As well as the usual input-output stuff up there. Apply kernel. This is one of the more interesting ones. I basically wanted one function where I can apply like any kernel I make, just so that I don't have to do it like multiple times. And well, it basically it works. If we go through it here, this is bold white. A simple boolean I used for making sure that if you have a picture that you want with all the colors, but some pictures where you apply filters you want them with only like white color, because otherwise, with line detection and stuff like that, it looks very strange if you have all the colors in, because you'll get these rainbow lines. Kernel size, basically, it's how large the kernel should be. Now, float kernel is the pointer address of the kernel, which is basically the referee to these little bad boys here. So I again don't really copy anything to the function, but rather use the thing I've already stored right in the bottom there. And then again, input output with the height as usual. We go through all the pixels apart from those that are within the kernel. So we start like, if the kernel is 3, we will start 1 pixel in on every edge. Now these here are the red, green, and blue. They are used for adding up the kernel. So I can use this shenanigan down here. And what this actually does is that this goes through each pixel and then multiplies it by basically the value. Okay. Let me phrase it correctly. You hit a pixel, and then what you do is you go through minus 1 here, and then stick that into this one. So you basically apply it to all the pixels around that pixel that we chose, which would be the normal x and y without this k, ky, and kx on. And then what you do is you simply add, you times it with what is in the kernel, and this is how I apply the kernel basically. And then you plus it together with the next one, and so on and so forth. What this basically does is that this will apply whatever value the kernel has. So if you stick in like 0, it of course won't be applied for that particular place. If you plan 1, it will have the weight 1, and so on, so you can give it more weights and less weights. What you basically feel like. To do this, however, it's very important to remember these resets, because if you do not have the resets, it will go in and it will continue to add this thing up, which will basically result in that in the end it will either turn totally white or totally black, most likely totally black, just because it will be like, oh, so I will base my value for the so basically if I hit the first pixel, it will go through the 9 pixels around that one, and then when I hit the next one, it will go through the pixels around that one but still be based on the previous ones. So it will be like continuously worse as you progress through the picture. This is why you reset them, so that it will be the new one for each pixel, not based on the previous values. That's just a random comment. So basically, if it's white, I want all of them to be the same, basically. Red, green, blue divided by 3, yada yada, as usual. If it's less than 0, set it to 0. This is to avoid going into funny colors, such as if it's a minus value, it will not go into, as you can have a kernel with minus values. That's why that's there. And then just set it to all the colors that it is. If it's not white, in this case, each color will be given its own color. Very, very simple, but interesting. And I've used this a couple of times for multiple kernels, which it works and it's cool. SNP is salt and pepper noise. This is a funny one also. Basically, what we do is we take an input-output as usual, and the width and height. Then we go through the entire picture again. Then we take the output is gonna be equal to the. This is basically making it grayscale again, just to make it better. I tried with not having this in, and then you get a picture where there is random red, green, and blue pixels like everywhere, and it looks kind of weird and doesn't really fit the name of salt and pepper. So, but back to original. What we do is we take this unsigned char n, and we say random modulus 100. So basically, if you take a random from the 100, and if it is under 10, then you will take another random, which is either 0 or 1. And if it's 0 or 1, it will be a random of a black or a white pixel. And that's basically what it does. And that's just applied to the picture once again. Then we reach the what? The do the pixel thing. Okay. I was a bit tired when I made this. I gave them some funny names. Let's see. This is basically pixelizing, or whatever it's called, where you make sure that the picture is like instead of having like normal 1 pixel, it will have like huge pixels, so it will look pixelated. That's what it's called. So you're given the size of what pixel size you want, in a sense, how many pixels you want that to be in one. Then it will go through the width and height according to this pixel size, and then it will go through this particular little thing, which is basically whenever we hit 1 pixel within the pixel size, we will set that to the input, and that will be that all of them will be set to the rectangle. That's why it looked funny before. Interesting. There's of course red, green, and blue, and as for red, green, and blue here as well. So it's like it will create a huge area of the same color, basically. Derp the Ripper. This is the making ripples in the picture. In my case, it's a horizontal ripple, which is just under your face and just above your face, which will make your head like higher and your chin stick out awkwardly, and it's quite funny. It's not perfect, but it works. We have the wave here, which is how powerful the wave should be. If you mess too much around with this, it will fuck it up. But I found a value that's specifically fine for this size picture. I am pretty sure it has something to do with how many pixels you have overall. I mean, how large the thing is compared to, well, yeah. Okay, so let's see. We go through all the pixels again as usual. We have the wave in, the input output, and the width and height. But we then go in and we're gonna go in and say we create these two doubles as well as these two ints. The double is going to be what creates the wave in a sense. So you go in and say the 20 times sine to the power of 3 times pi times the float of x divided by 128. What you do here is that you go in and say that the output of the x, so what would have been the normal value of this particular x pixel will now be with the nx, with the new x value. So it will move it basically. This is how you create where it should go, and this is just to place it in. That's basically what it is. Then I have this tiles thing. I found most of it. It's done in a peculiar way, and it doesn't look as nicely as I would have wanted it. It has some major flaws, but I will show it anyways. Alright, so tiles thing. So basically what we do is that we create these two new height and width. We go through the original picture, and then we take in and of course the color as well. And then we take in and create these two new floats, which is called new factor of x, and the new width, which is equal to the new width divided by the float of x. So this thing up here, and we do that for the same, and then we divide it by we divide the new, we create a new one again, so a new x, and divide the original x with the nfx. This is a bit strange way it is done, but it's slightly it's not perfect, but it is a way to do it. And then what we go in and say is that we go in and say, okay, so the output of this particular pixel is going to be the input int of the new nx, new y times w, and the new x and the color free. I will show you how it works, and then you can see that it's not perfect, but it works. And then the sepia, which is basically turning the picture into sepia. It's like you get this slightly orangey looking thing, which is, I don't know, black and whitish. The specific formula for doing it is this. These numbers here are what does the magic for sepia. These are some numbers I found for it, and they seem rather legit as you complete do it. This part here is what makes sure that if what the sepia can do is that it can go outside the normal range of what the pixel value should have, meaning that if you have like a white pixel, it can go increasingly beyond 255, or if you have a black pixel, that it can go under 0. This will make horrible mishmashes, so that when you have the light and it should be orangey, if you have very much light in one area, it will become blue due to like jumping out of scale. So this is to make sure that it stays within scale. It's basically putting a limit. If it's less than 0, set it to 0. If it's higher than 255, set it to 255. And then you just stick these out. Basically what you do is you take in the input of the red one, times it by this value, plus the blue, plus the red, plus the green one times this value, plus you basically weight each of them differently for each of the colors, and that magically creates sepia, basically. Okay, so now I will send you off to showing what's actually in the how it actually looks like. So here you can see everything running at the same time, which is basically what is the cool thing about it. So first of all, if we go to this corner up here, you see the original image, As you can see, there is a slight delay. This is of course consisting that we run all of these at the same time on my relatively crappy laptop, but the fact that it still runs relatively smoothly is okay. I'm going to lift my hand up. You can see that there is, well, maybe you can't see that there's delay, but I can. Just a little bit. In any case, we move on to the next picture, which is the mirrored image. Me moving like slightly, I can slide into myself here. Then on to this is the grayscale. In this box here, we have the red, green, blue, which is filtering all the colors, all the other colors out. Then we have here the detection of red, which you can see there. There's red in my face, as well as this. This is a pink clock I have, as you can see here, as you can see in the other picture here. And it is detected as being, well, slightly more red than the rest of the background. Then we have the green. I don't think particularly I have. Ah, yeah. See, this is very, very green here. It's a huge green stick. Let's see. And then of course we have the blue, which is like I have a pencil case, which is very blue. So that's detection of all three colors. Okay, moving on. This is the cropped one, where we have a skewered down to only taking the middle, so you can only see my face like now. Then we have the inverted. Then we have another one, which is rotation. This is basically the 30 filters, each and every one of them. This is the inverted one. I just took it and rotated it, which is also an operation. Then we have the mean filter, which is the I can show you that here. Whoops. This is all the applied kernels, and we start with the mean one. Then we have the edge detection, the Sobel, the Shard, Sharp. Do I even have the? Yeah, the Sharp is yeah. And that's basically all of them we have. So we go back to saying, okay, so we have the thing here. This is the sharpening. This is the edge detection, which has it has a decent amount of what is it called? This is the Laplacian thing, which is it's very nice, but as you can see, it has a decent amount of noise on it, but it's still very very clear. Then we have the Sobel down here, which is very good also, but has a very very distinctive. It looks so depth affected that it's really really weird. We go to the sharpening image I made here. As you can see, it is relatively sharper in the fact that it cuts a bit down on the light, but it also has a lot of noise. I haven't really fixed this because I didn't have time for it, but it is possible. Here we have the, let me just check what that one is because I can't remember. It is the Gaussian filter, which is again a blurring filter just like the mean. And then of course we have this is the 5x5 Gaussian, this is the 7x7 mean filter, and that disk as well, which you can see is even more blurred than the one right beside there. And then we come to the fun stuff. Oh, actually, let's just take the boring stuff down here first. This is again this is the rescaling. As you can see, it is exactly the same as the mirror image. I based most of them on this one. It looks like the crop, but it's not. It's squeezed. It's smaller. Then we have as you can see here, the salt and pepper noise, the pixelation, which is, and then my very very manly chin down here, which is the rippled and the pixelated. I like the pixelated part. It looks really fun. Stuff. Then we have the tiles. As I said, you can see here how it messes up, but it is tile based, so meh. And then the sepia, which is actually really really nice, and as you can see, it makes this slightly yeah, slightly oldish. Now to the fun stuff. These 5 here, or actually these 7 here. These 2 pictures are not per se filters. This image here, the one here is the first picture. This is the second. You can't see it when I do like this. But there is a difference between the two. What you can see is on this thing. This is the base filtering. This is the background subtraction. When I move, there is a difference between the two, which becomes white. If I sit perfectly still, if I can sit perfectly still, I'm almost invincible. Invisible. Which is very, very cool, and I like it really, really much. It was very successful when I made this. Then, of course, I've applied erosion and dilation to these, as well as opening and closing, just to show those two. Up here, in these two, we have this is called, what's it called, closing, because what we do is that we take the white pixels, we first dilate them, so making them bigger, and then we erode them to make them back to original size. Which basically closes the holes between the white pixels. As for down here, we have the what's it called, closing, which is erosion first and then dilation, which closes in the small pixels, basically removing the noise from this picture, which was the original white. As you can see, I can move my hand around here. Now you may have noticed the tiny green circle here. This is the center of the mass, which I just used for this one background subtraction. So when I move my hand like this, it will follow the middle of all the white pixels, basically following my hand as I move it around, if I remember not to move anything else. And that's pretty much it for my 30 filters. It was very fun to make it show all of them at the same time, because it's kind of challenging, and I'm very happy that it succeeded. Thank you for watching. I hope you found it entertaining.